All right, Chapter 8, Section 3, Day 2 on similar polygons. In Day 1, we talked about what makes, so if we are given this designation, this name, this title of similar figures, what kind of baggage comes along with that? Because, yeah, sure, great, it has a specific name, but what actually can I do with that information? And we learned about two main theorems that are tied to the fact that objects are similar to each other. And they have to do with corresponding pieces. That term corresponding refers to same relative position, because we are ultimately talking about two different figures, like what you see here on the screen. I have two separate triangles, and even though they may be dilations of one another, dilation, again, the term that we talked about in section 1, where this is a miniature version of this one, or you could think of it in reverse, where this is a magnification of this one. Whichever way you think about it, they are still two separate shapes, right? And when I give this designation that these two shapes are similar, there is certain baggage that is tied with that. And again, it all gets back down to corresponding pieces. Okay, if I think in terms of something that's familiar to us, like a child's toy, like say a Hot Wheels car. If I had a Dodge Viper Hot Wheels car, this really cool looking Hot Wheels car, it's a miniature version of an actual Dodge Viper. And what makes it look so cool, so real to a child, is the fact that it is a scale model, a dilation of the actual real life-size thing. So corresponding pieces, like say the tires or the windshield or the grill or the hood, whatever it might be, they are scaled down versions of the actual real measurements. Okay. And so we see the same thing here with simpler shapes like triangles. And we learned about two theorems about those corresponding pieces. First of which, angles have to be congruent. More specifically, corresponding angles have to be congruent. Again, same position. Why is that the case? We use simple shapes like triangles because there are only a few things that we need to measure. If we get more and more complicated shapes, the same rules still apply. It's just I have to kind of redundantly do it over and over again for more and more angles. Like if I gave you octagons instead, now I'd have to confirm it with 8 different angles as opposed to just the 3 that I have to do in this case. But in any case, whether it's a triangle or a more complicated shape, the angles have to be congruent, corresponding angles. For instance, angle D and angle M here are corresponding angles. They would be the same relative position in each other. So if I were to magnify this smaller triangle and put it on top of this guy, angle D and M would line it up. And those alignments, those corresponding angles have to be the same measurement in degrees. Why is that the case? Because the angle measurements ultimately determine the shape of this polygon. Okay, there are lots of different ways for me to draw a triangle, and the angle measurements kind of dictate the shape of that triangle. Okay, the fact that this is a dilation of this one means that all 3 of the corresponding angles have the same exact congruent measurement, whatever those may be. And then the second rule that we learned had to do with the side lengths. This is where we really see the difference in the actual size of our figures. Okay, side length, if angle measurement dictates what the shape of a given polygon is, like how wide it may be, or like whether I have acute angles or obtuse angles or right angles, all those sorts of things, it dictates the shape of that polygon, whereas the side length will dictate the size of that polygon. There will be a very big difference from a Hot Wheels car, which is 2.5 inches long, versus the real life Dodge Viper, which is closer to like 9.5 feet long. Okay, so the size of the actual shape, the object, is going to be dictated by the scale factor that is made between the two objects. And what we learned in yesterday is that this change in size can be measured by what we call scale factor, and we represent it with the letter K. And the rule is that, for instance, this side here, DE, which corresponds to MN here over on this side, whatever multiplier expanded or magnified this 15 to increase it up to 18, whatever multiplied by this side to make that side, has to be the same multiplier, the same scale factor as whatever multiplied by DF down here to make it MP. Okay, so and the same thing would apply from EF to NP, right? And that's what's ultimately going to give it that similar shape. Okay. Because if I had different multipliers, namely if I multiplied this 15 by something and I got 18 and I got multiplied by 20 by something, I got something different, there would be a noticeable difference in the actual dimensions of my result. Okay, kind of like if I looked at a Hot Wheels version of a Dodge Viper, if it had like a weirdly shaped windshield, or like the tires were too big, or the hood was too long, or something like that, there would not be a very accurate scale model, and it'd be pretty noticeable. We've all probably seen like bad knockoff versions of those children's toys where we're like, oh god, the scale is off. Right? Case in point, if we think about the Barbie doll, okay, there are some pretty funny memes out there that if you were to take a Barbie doll and actually scale it up to a human size, they would look like an absolute freakish alien, because no human has those dimensions, whether it be the size of the eyes relative to the head, or the length of the legs relative to the body, or the size of the feet. Okay, it's pretty comical. I recommend checking that stuff out. But in any case, if the scale is off, it will be noticeable. All right, so back to these problems. I'm going to end up doing just like the quick solutions and mostly just talk about where that stuff comes from, because the actual way to solve these is very, very fast. So we'll be doing two examples. This is the first of which you're going to be told that you have similar polygons. And I'll tell you right now that triangles will be the most common shape that you are given, just because it's the simplest to draw and deal with. And you're going to be given some information, whether it be side length or angle measurement or whatever, most often side length, because we're dealing with scale factor. And you're going to be given variables somewhere throughout the diagram, maybe in one place, maybe in multiple places, whatever it might be. And you're going to be asked to solve for that variable. And we're going to use the concept of proportionality, the fact that there is a scale factor and a constant scale factor, to figure out how to solve for that variable and set ourselves up with a simple algebraic equation. So let me jump right in. Here in this problem, we are given the following triangles: triangle DEF and triangle MNP. We are told that they are similar to each other. So immediately they have those two theorems that tag along with them, namely corresponding angles have to be congruent. And there's no information given to me here about the angle, so it's not really useful in this context. But then the second one, which we will be using here, has to do with the side length. And namely, the fact that whatever the constant multiplier is that takes this 15 and multiplies it by something to give me this 18 has to be the same constant multiplier that takes this variable, whatever this ends up being, to multiply it to make it 30. And so we'll be able to use that to make an equation. And we're going to use a little piece of a proportionality statement. Namely, we're going to do this. Since my ratio, my constant of multiplication, my scale factor, has to be the same for each of these sides to each of the other relative sides, this will look a little familiar, where I could compare side lengths to side lengths of other things. And whatever the ratio is from one side to its corresponding side has to be the same for the other sides. And so that constant here is going to be K. Now, in this case, it actually doesn't ask me to solve for what K is, so I'll just get rid of that. So I'm just going to be comparing two ratios. And in this case, I definitely want to solve for X, so I want to have X in one of my ratios. Okay. And what I'll be doing is I'll be plugging a variable into an equation and thus being able to solve for that variable. So in this case, for the sake of like direction, let me put X here in the numerator just for the heck of it. So I'll put X up here. Great. All right, so I want to ultimately plug in the correct pieces and stuff here. So this X has to correspond to some side here in this triangle. Now, since it's convenient that they're oriented the same ways, it's pretty easy to locate that EF here is corresponding to NP here. So X is going to be corresponding with this 30. And so because they're corresponding pieces, they'll end up in the same fraction. Okay, so this is where I'll emphasize that corresponding pieces will be in the same ratio. Okay, EF and P are corresponding pieces to their respective triangles. They're in the same fraction. And then I need to compare it to two other sides, some piece and its corresponding piece. And it doesn't actually matter which other pieces I use, as long as I have enough information to use. And in this case, I could either use DE compared to NM, or I could use DF compared to MP. And it doesn't actually matter which one I use because it should be the same scale factor either way. So let's use DF down here on the bottom. Okay, DF here. I'll start with this one. This one's going to have to be on the numerator for this reason. X and 20, the numerators here, are part of the same triangle. Okay, kind of like when I solve scale factor and the numerator has to be my image measurements. In this case, X and 20 are my image measurements. So now on the denominator, these are going to be what we would consider my original measurements. So technically in this case, based on how I'm setting up these ratios, I'm going from this triangle and minimizing it down to this one, just to kind of use the context here. In this case, when I'm solving for the variable, it actually doesn't matter which order I go as long as I'm consistent. But now I need the corresponding piece to this DF. So what corresponds to the 20? The 24, MP over here. So here's where, again, I'll emphasize where like the trickiest part here is like making sure stuff's in the right spot, because there are technically 4 spots to choose from here. The X, I just usually start with it in the numerator in my first fraction. So if that's the piece I'm solving for, that's where I'm going to put it. And then I need corresponding pieces in the same ratio, in the same fraction. So these two have to correspond to each other. These are 2 separate figures, 2 separate triangles here, but they're corresponding pieces. So the X corresponded to the 30. That's my first fraction. As far as what are my numerators, those are the pieces within the same figure. So notice the X and the 20 are in the same figure. Same thing with the 30 and the 24. My denominator have to be from the same figure. 30 and 24 are in the same figure. Okay. All right, now that I've set myself up with this equation, now I can actually go about the business of solving for my variable. And we're going to use a technique here that hopefully you are familiar with. This goes back a ways into probably some early on algebra classes that you dealt with, definitely in middle school. But anytime I have a fraction equal to a fraction, just like we're going to deal with quite a bit in this unit, anytime I have a fraction equal to a fraction, I can use a technique called cross multiplication. And most of us can immediately infer what to do at that point, but let me just walk through it. So I'll cross multiply both of these figures. So if I multiply 24 times X, let me just rewrite this over here, 24 times the X on the left, and then multiply the 30 and 20 here on the right. Ran out of room there. Okay, so there's the cross multiplication process. At this point, now it's just regular algebra. So 30 times 20, I'm going to get 24x is equal to 30 times 20, which gives me 600. And then in order to solve for x, I just simply divide by the 24. Don't be a hero here. Feel free to use calculators. So using a calculator, that 600 divided by 24 gives me 25. So x has to be 25. Ran out of room here, so let me throw this over here. X is 25. And that's, again, that's done by dividing both sides right there. Okay, so what? What does my result mean? So first off, that tells me the length from E to F, and it makes sense that 25 here is less than 30 since all the measurements here are respectively smaller than each of these guys. So far that checks out. Now, did I do the correct scale factor? That can be confirmed by putting this 25 back into my original ratio comparison. So if this was 25 over 30, 25 over 30, I could reduce that fraction. 5 would go into both top and bottom, and I get 5 over 6. Just confirming that that does in fact equal the scale measurement here. 20 over 24, 4 goes into both of these, and that would reduce again to 5 over 6. Thus giving me a constant scale factor. And so what does the scale factor of 5 over 6 actually mean in this context? That would be like taking this original larger triangle, multiplying the whole thing by 5 over 6, thus reducing the size to this guy here. So that's what that would mean. But again, the punchline of how to solve these, you're going to set yourself up with ratio comparison, where you're comparing one fraction to another. Just make sure that in each fraction, these are corresponding pieces. Okay, each of these are corresponding pieces. 20 to 24, x to 30, corresponding pieces. And then left to right, numerators are in the same figure, denominators are in the same figure. So x and 20 are in the same triangle, 30, 24, same triangle. All right, let's move on. Our second example for the day, we're given the following. Okay, and we're told the same kind of information. We are told that we have two similar triangles here, namely the smaller triangle RTP here on the left is similar to XPZ here on the right. This is the smaller of the two, so this would be magnifying RPT to make XPZ, or I would start with XPZ and say, all right, this is a reduction from XPZ down to RPT. So at this point, you'll notice there's a little bit different presentation of information here. Namely, I'm given this little red line with these little boxes implying perpendicularity or 90-degree intersection. And here's where I'm going to reference back to the kind of more fundamental definition of two similar figures. If two figures are similar to each other, like these triangles are similar to each other, that means corresponding pieces are scale versions of each other. Much like with, again, the Hot Wheels example. If I tell you that a Hot Wheels version of a Dodge Viper is a smaller reduction scale version of the actual real Dodge Viper, not only will the length of the car be some constant scale factor K smaller than the actual length of the real life Dodge Viper, but so will the height, so will the width, so will the size of the steering wheel, so will the height of the wheels, so will the size of the engine. Okay, everything kind of falls in place after that. So not only does it mean that just the side lengths of a given triangle, the three side lengths of a given triangle are similar or scale factors of another, but also the other pieces that are corresponding as well. In this case, both of these little red lines here, these perpendicular red lines, are what we call heights or altitudes of their respective triangles. Okay, and for those of you that have done geometry units in the past, or you've solved for like the area of a triangle, you've probably seen these before. And when I measure the length of this case, because it's just on the side, when I measure the height of this triangle, I need a perpendicular distance from one base to its opposite corner. Okay, so in any case, what the important thing to understand here is that these are, in fact, corresponding pieces. They just happen not to be one of the three sides of the triangle. But the same rule will apply. They have to be scale factors of each other. So I'm going to use the same exact technique that I did in the last problem. Namely, I'm going to be comparing two ratios together that have to share a common scale factor. And again, the same rules will apply where in each of these fractions, in each of these ratios, they're going to be corresponding pieces. So whatever fraction this is, they have to be corresponding pieces. These have to be corresponding pieces. Numerators have to be from the same figure. So since I'm dealing with two triangles, say for instance, these numerator pieces will come from triangle RPT, whereas these denominator pieces will come from XPZ. Okay, and then again, within each individual fraction, they have to be corresponding pieces. So let me start with my variable, much like I did last time. Okay, I need to solve for X. Let me throw that in my first numerator. It doesn't actually matter where I end up putting it, but for the sake of consistency, I'll put it there. All right, so again, in the same fraction, these have to be corresponding pieces. X here happens to be the height, or this perpendicular part to triangle RPT, meaning I need to correspond with the height or perpendicular segment here of XPZ, namely this 20. So X and 20 are corresponding pieces in the same fraction. All right, numerator-wise, this X was part of triangle RPT. So my numerator over here must also be part of this triangle. Now, I actually have a couple of options here, much like I did in the last example. In this case, they actually break up this side TR into two little pieces, namely from each corner to that center piece of that perpendicular intersection. So I could either focus on one of those pieces as long as I have the information about the other side, which I do, or I could take the whole side length of R to T, namely just adding those two together. This whole side length here would be 12. It doesn't matter which one I do. For the sake of smaller numbers, I'll use just the 6. So again, X, the numerators have to be in the same triangle or the same figure. So since X was in the numerator, I'll use a 6 right here. All right. In this fraction, they have to be corresponding pieces. So now I'm going to look over here. Again, denominators have to be in the same figure as well. So the 20, I'm going to be dealing in this figure. And because I'm dealing with corresponding pieces and I used this little piece right here, I got to use the little piece right here. So I'm going to compare it to that 8. The reason I bring that up is because maybe I was shown like, hey, that's 6 and 6 on this side, but then I was just told like the whole side length here was 16, in which case if I just use the 16, then I would want to use the whole side length here as its corresponding piece. It'll just kind of depend on the information you're presented with. So in any case, as long as they're corresponding pieces, use that information. All right, but now I have a fraction equaling a fraction. I can use my cross multiplication technique. So I'll multiply 8 times x and 20 times 6, and that will give me the following. 8 times x gives me 8x, and then 20 times 6 here on this side. I'll go ahead and do that math. Again, feel free to use calculators, but 20 times 6 gives me 120. And again, I still have 8x here on the left. If I want to solve for x, I would divide both sides by 8, and I will get x equals 15. Feel free to confirm that on a calculator. But there's solving for my variable. Just doing a couple quick things. Sanity check. If 15 was back in this diagram, it makes sense that these measurements will be slightly smaller than these guys. So that lines up. If I ended up with a bigger number than that, then I might want to double check my math. In that case, I might have messed up the order of what should have gone where. If I actually plug the 15 back into my ratio here, so this was 15 over 20 reduces, 5 goes into both, I'd end up with 3 over 4. So my scale factor would be 3/4, just confirming that it matches what's over here on the right. 2 goes into both top and bottom, and I get 3 over 4 again. So what is the meaning of that scale factor K, that 3 over 4? That would be taking this larger XPZ triangle, multiplying it by 3/4 to get this slightly smaller RPT version of itself. All right, and those are our 2 examples for today. What I wanted to end on today was to talk about higher dimensions in scale factor. And to do that, I'll just kind of illustrate something really quickly for you, just so you can kind of understand what's going to happen. I'll describe what you're going to see in terms of problems for that sort of thing. So let me start with taking, say, a rectangle. Okay. And I'm going to increase this or magnify this by a scale factor of 2. All right. So I'm going to double the size of this rectangle. So we might want to know some of the actual measurements. Let's say that this was, say, I don't know, 3 units by 2 units. Okay. So this is my original rectangle is a 3 by 2 rectangle. And I'm going to double the size of it. In other words, I'm going to use a scale factor K of 2. Right. So let me write that off to the side here. I'm going to use K equals 2. So what that literally means is that my scale factor is 2, meaning that I am literally doubling the size of this original figure. So it should be magnified. Okay. So before I magnify this, let's talk about some higher dimension measurements. The 3 and the 2 are what we call one-dimensional measurements. Length, right? 3 units, whatever those units may be, whether it be centimeters or miles or whatever. Okay, that 3 units is a simple length. That is what we call a one-dimensional measurement. The same thing would be applied here for 2. It's like you pull out a measuring tape and you measure that to be like 2 feet. Okay, great. That's a one-dimensional measurement. A 2-dimensional measurement would be finding something like area. The area of this rectangle or the space on the inside, maybe this represented some fence that you were trying to do. You were trying to build a building or do something in your yard. This 3 by 2 section, if I want to figure out how much space is on the inside, I would simply multiply length times width. And I would find out that in this case, 3 times 2 is 6 square units on the inside. Okay, 6 square units on the inside. I'll use lowercase u for units. Okay, 6 square units. Again, just length times width. That's a calculation we're all familiar with. All right, but now let's apply the scale factor. Now, the one-dimensional change is going to be pretty straightforward because if I double this 3-unit length here, it's going to become 6 units long. Okay, so there's another 3 units here. So my new length here will be 6 units. Let me just do that real quick. All right, now if I extend this side by multiplying again by the scale factor of 2, then that becomes another 2 units right here, or 4 units. Okay. And what I've created is I've created this new rectangle that is double the size of the original. And here's what I'm talking about. So each of these new measurements, this 4 by 6 now, was simply taking a one-dimensional scale factor change. Take the length, double it in this case. K could have been anything. It could have been 17, in which case it's becoming 17 times the size. And it's just a simple multiplication. I take my scale factor, multiply it by my one-dimensional length. That tells me my new one-dimensional length. But let's look at the higher dimension measurement here, area. Let's look at our new magnified rectangle right here. If I were to multiply length times width for that larger rectangle, namely 6 units by 4 units, I find out that my larger rectangle has 24 units squared. And the reason why that's unique and why it's interesting is because look at how these square units changed. The original figure had 6 square units, and if I doubled the size of it, notice that instead of doubling the size of my area, it in fact multiplied it by 4. Okay, that is worth noting because this was a 2-dimensional measurement. And let's say I added a depth to this, like this was some sort of tank or like a bathtub or something like that. And I was filling it with a fluid. All right. So if this was a bathtub, a 3 by 2 bathtub, a very, very small bathtub, more like a sink or something like that at that point. But if I was doubling the size of it to the 6 by 4 bathtub, and maybe I gave it a depth of a single foot. Okay. So it's a 1 foot deep sink or something like that. And I was doubling the size of it. Then that 1 foot depth would double to 2 feet depth. And when I'm talking about a 3-dimensional measurement, now I do length times width times depth. And what you would find is that my new 3-dimensional volumetric measurement would instead go from 6 to 24, and then it would go times, then it would be 48 cubic units. So let me come back to that in a second, because we're not going to deal with the volumetric measurement as much. But let me just kind of break it down this way. A one-dimensional measurement, when I'm scale factoring, I simply multiply by K, my constant of scale factor. So a one-dimensional measurement, for instance, for us would be something like height, right? If I was going to turn you in, like to make a G.I. Joe or a doll version of you, and I want to scale factor it something down, reduce obviously the size, and do like, I don't know, a 1/5 scale version of you so that you had like a little doll of yourself or something like that. Okay, that was 1/5 your size. And let's say your one-dimensional measurement was like, say, taking your height. If you were 5 feet tall, right? If you're 5 feet tall and I do a 1/5 scale version of you, I would multiply that 5 feet by 1/5, and I would find out that my doll is 1 foot tall. Okay, that's a one-dimensional measurement. But for area, which is say a 2-dimensional measurement, area might be for something like clothing for that doll, right? And if I were to take like the material that you use for your shirt, so I'm looking at square footage of that shirt or something like that. Okay, what I'm going to end up doing is I'm going to be doing K squared, 2-dimensional, K squared. And so for something like this, if I'm trying to figure out how much material to use to make like a t-shirt for this doll, and I had like figured out that your t-shirt was say something like, I don't know, 6 square feet of material, and I was doing a 1/5 version of that, then I would need 6 square feet times 1/25 of that. So where did that 1/25 come from? If it's a 1/5 scale, 1/5 squared would be 1/25. Okay. And again, we're not going to need this dimension in this section, but for 3D, so for something like fluid or like creating, like if I was going to put that doll in a box and I need to figure out how much space was in that box. This is where, since it's three-dimensional, I'm going to take K and cube it. And 4 dimensions would be K to the 4th, 7 would be K to the 7th, so on and so forth. Not that we're going to deal with that stuff at all. But from a volumetric standpoint, whether it's filling with a fluid, a gas, liquid, whatever it might be, okay, then it would be K cubed. So if I had a 1/5 scale, 1/5 cubed would be 1/5 cubed, or 1/125. Okay. So that's just kind of the thing that you're going to be dealing with on a couple of problems. And again, reference back to the notes. I do a little bit of an illustration like this off to the side. Again, you're not going to be dealing with the 3D version as much, so you will see this 2D version with area come up. So be careful of that, because it's dealing with a K² version of that. All right, so I'll go ahead and stop recording there. That will conclude our section 3 notes. There we go.